Hi everyone, I'm Indrani Rawat, Administrative Coordinator of ASHRAE India Chapter. On behalf of ASHRAE India and ASHRAE Rajasthan Chapter, take the privilege to host this webinar and happy to welcome you all. I also thank Osama Khayata, RAL System Administrator, for organizing the session. First of all, I request everyone to ask technical questions by clicking on question button or panel button from your headset. The speaker will be answering at the end of the session. Today, our speaker, Mr. Krishnan Vishwanathan, and I have with ASHRAE since 1989. In the year 2006 to 2007, he was the president of Western India chapter. Since then, he is actively working for ASHRAE. He has also served on a presidential ad hoc committee to draw up the bylaws and manuals for the region at large. He is also involved with ASHRAE since 1986. Today, he will be sharing his expertise on the topic of current trends in room air distribution. Thank you everyone for joining. Now over to Krishnan sir.
Thank you, Indrani. Thank you very much for that very brief introduction. Appreciate that very much. And I'd also like to thank Osama for helping us put all this together. Osama is our coordinator from region at large, and I welcome all of you this Saturday afternoon for a small session on the current trends in room air distribution. What I'd like to do before we actually go is to have a couple of slides which we normally, as a matter of practice, present at all ASHRAE meetings, and that's the ASHRAE Code of Ethics. I just read the ASHRAE Code of Ethics. In this and all other ASHRAE meetings, we will act with honesty, fairness, courtesy, competence, inclusiveness, and respect for others, which exemplify our core values of excellence, commitment, integrity, collaboration, volunteerism, and diversity, and shall avoid all real or perceived conflict of interest. Before we get down to the topic, as is customary at all ASHRAE DL and the regional lecturer programs, we do a little presentation on what ASHRAE is all about and the ASHRAE CTTC. So this is what our real objective is: to teach, to network, to share, to learn, and by doing all of that, we grow. So participation in ASHRAE activities is an excellent way to advance your career, both technically and personally, and from a business perspective. If you're involved in the HVAC&R field or a closely related field, ASHRAE is really the go-to organization for professional advancement. Help ASHRAE share the industry, advance research, and disseminate critical information. It's possible to really use ASHRAE as an information resource and not contribute to the development of that information. That's possible, but not nearly as fulfilling. ASHRAE really thrives on the volunteerism work which thousands of professionals like you bring into the society. Don't really treat ASHRAE as a spectator sport. Participate. Opportunities are all around you. Explore the ASHRAE website, and you will realize what are the various opportunities that are available to you. You may not realize it, but you might be the expert in some area that could be valuable and provide additional value to ASHRAE and its membership. So program ideas, research ideas, handbooks, standards, student mentoring, all these are areas in which I'm sure that in some way each of you would be able to participate and grow. With that, let's turn to today's presentation. And today's presentation is we're going to spend the next hour and a half to look at the room air distribution. And we're going to look at it primarily from the point of view of comfort. We're not going to focus so much on industrial applications or specific applications which might pertain to specific needs. But for the large majority of people who are in the business of air conditioning, comfort is something that's paramount, and maintenance of comfort is what really drives the whole air conditioning industry to keep people and processes going. Now, these are the comfort limits which are set by ASHRAE. Now, this little chart that I'm showing you is something that dates back to 1992. The ASHRAE Standard 55, when it was written in 1992, really spec'd in these numbers. So we talked about what are the kind of numbers that we ought to have in the occupied zone. So we had looked at, or in fact, these are the numbers which come down even today. Most of us still work with these numbers and they become like paradigms. So the temperature in the occupied zone, 73 to 77 degree Fahrenheit, RH anywhere between 25 to 60%. Generally, everybody works with about 55 plus minus 5%. And we recommend that in the occupied zone, we have air velocity of about 50 feet per minute if you are cooling, and not more than about 30 feet per minute if you're heating. The comfort standard which got prescribed then also permitted us to have a temperature gradient of about 5 to 6 degree Fahrenheit from the floor level up to the top of the occupied zone. So these are numbers which you can keep at the back of your mind. Most of you will be familiar with all these numbers because this is probably what you work with day in and day out. However, if you look at the current standard that ASHRAE is looking at, that's the last edition, it gives you a bigger leeway to play with. So it actually tells you in this diagram that you see, you could actually work at much higher temperatures instead of the numbers that we looked at earlier. We could go to higher temperatures, and provided we are able to have some kind of control on the airspeed in the occupied zone, which corresponds to a higher airspeed at an elevated temperature. Now, why do we sort of move away from the earlier paradigm? Primarily because of the fact that we're trying to maintain comfort, at the same time trying to look at what is the kind of saving that might accrue to us from the energy standpoint if you are able to operate at higher air speeds and higher air temperatures. Now, the current standards don't really prescribe any minimum air movement in the occupied zone, long as the temperature in the occupied zone is acceptable to the people. So today, of course, increasingly people are talking about trying to maintain temperatures depending upon where you are, and we talk in terms of adaptive comfort, etc. The whole focus really is on maximizing the energy conservation. So you try to maintain a temperature which is acceptable to the people in the occupied zone. At the same time, try to see what is the lowest possible airspeed that you need to have in that occupied zone so that people feel comfortable. Now, the air motion in the occupied zone really is a function of the discharge velocity. So when I say discharge velocity, what I really mean is the velocity of the air at the outlet of the supply air, the supply air outlet. As the air is leaving the supply air outlet, what is the actual velocity that you measure perpendicular to the direction in which the air is flowing out? So discharge velocity is determining what is the kind of velocity you will have in the occupied zone. The discharge air temperature also plays a part, because all of you are familiar with the laws of buoyancy. So if the temperature of the supply air or the primary air is lower, as it would normally be when you're air conditioning, being denser, it would tend to come down. So the larger the differential temperature between the room air and the primary air, the faster it's going to come down. Similarly, if your supply air temperature is higher, the primary air temperature is higher than the room, typically when you're trying to heat, then the air would tend to rise up. So this thermal buoyancy also plays a part in what will be the velocity of the air in the occupied zone. Coupled with these two things, the other thing that would play a part is what is the kind of air diffusion device that you're using to supply and deliver the air into the occupied space. Now, this would really depend upon whether you are trying to supply the air from the ceiling. In other words, if you're using a ceiling-based air distribution system, or are you going to supply it from the sidewall, which is typically in case we are looking at systems which are most common, that's the mixing air systems. But you might have other systems as well, typically displacement ventilation or underflow, where you would be supplying from the floor or from the sidewalls. So these are the three parameters which really determine how the air would actually be moving within the occupied zone. Now, the relationship between room air movement and occupant comfort. Now, this can best be illustrated if we take a step back and think about the days when air conditioning was not so commonly used. Maybe many of us grew up without having access to air conditioning at homes. So if you went out on a hot summer day and you got back home, you obviously felt very hot. The first thing that you did really was to switch on the ceiling fan. And why did we do that? We did that simply because we felt cooler when the fan came on. So does it really mean that by switching on the fan, we are lowering the temperature? No, we're not. All that we're doing is increasing the flow of air over our body. And by doing that, the increased airflow is able to remove the heat away from our body. It's able to carry it away. So the feeling of coolness is created by increasing the flow of air over our body. In other words, we are increasing the airflow over the body. We are increasing the air velocity. So the fan is effectively increasing the local air velocity. So the faster you put the fan on, the faster you tend to feel a lot better faster. So that's the feeling of coolness that you get by just increasing the air velocity. There have been empirical studies done, and it's generally established that a change in velocity of about 15 feet per minute in air velocity produces approximately the same effect on comfort as a change in temperature of 1 degree Fahrenheit. So to put this in perspective, if we have a room with a fan on, if I'm able to increase the speed of that air over my body by approximately 15 feet per minute, then it feels as if I have actually reduced the temperature by 1 degree Fahrenheit. Actually, you are not reducing the temperature, but you get that feeling. So it's a perception. So this is actually the relationship between the velocity of air and the feeling of temperature. So room air velocities are generally recommended as, for example, ASHRAE. If you look at the ASHRAE fundamentals and the ASHRAE applications, it will recommend that you maintain a velocity of about 50 feet per minute in the occupied zone when you are cooling, and not more than 30 feet per minute if you are in the heating situation. Now, like I said, in today's context, we are not really sticking to these numbers. All that we are saying is that try to have a velocity of air so that people feel comfortable. You shouldn't be feeling, it shouldn't appear as if you're walking into a stratified zone where there's absolutely no air movement. So even though the temperature might be low, because of the fact that there is no air movement, you tend to feel very uncomfortable. But the fact remains that any velocity lower than about, in a cooling situation, any velocity lower than about 30 to 20 feet per minute is generally not perceptible. So you want to make sure that you're operating anywhere between 40 to 50 feet per minute, provided, of course, that the temperature is not more than 75 to 76 degrees Fahrenheit. So if you were to actually think of a situation where you want to raise the supply temperature and maintain maybe around 78 to 79 or even 80 degrees Fahrenheit, you could well do that, and then have this air velocity in the occupied zone go up to about 80 to 100 feet per minute. So that's something that you can do very comfortably. Now, there is a method for us to actually calculate what is the effective draft temperature, and that is given by this simple equation, which you see in front of you. So I've got the one that you see in green is for IP units, the British units, and the one below that is for your SI units. So effective draft temperature, what you need to do is to measure the local air temperature at a particular point, which is designated as Tx, and the control temperature is the temperature that you're trying to maintain in the space. So typically, if you're saying that you're maintaining 75 degree Fahrenheit, then control temperature would be read off as 75 degree Fahrenheit. And Vx is the velocity of the air, either in feet per minute or meters per second, depending upon which units you're working with. So you need to really measure the velocity at the same point where you're measuring the temperature. Now that's a key. So once you have all these numbers, like you already know what's your control temperature. So all you need to do is to measure the local air temperature and measure the air velocity. So you need to measure it at the same point simultaneously. And once you have that, you can plug it in and you'll get a result for the effective draft temperature. And studies have shown again that a high percentage of people, particularly in sedentary situations, are very comfortable when the effective draft temperature lies between -3 and +2 degree Fahrenheit. Okay. Now this, when I'm saying -3 and +2, this obviously refers to the first equation that you saw there. That's for your British units. And in case you are working with SI units, then your it will lie between -1.7 to +1.1. Now this pertains to cooling, both these data that I provided you with, that's -3 to +2 and -1.7 to +1.1 degrees Celsius would be corresponding to a cooling situation. Now if you're in a heating situation, then the formula changes slightly. If you need that formula, you can go back to the latest edition of the ASHRAE Application Manual 2019, refer to chapter 58, and you will get that formula. And the same parameters will apply. That in case in the case of a heating situation and you're working in British unit, then the answer lies between -4 and +3.6, and in heating between -2.2 to 2 degrees Celsius, then people are generally comfortable. Okay, so this is really what we use to figure out how effective an air distribution system really is. So that brings us to the concept of air diffusion performance index. So what we actually do is, let's assume that we all of us are sitting in one classroom, and we have, let's say, about 30 people in that class. So what we will do is, once the system is in operation, we would actually take the measurements of our the local air temperature and the velocity around each person. Maybe we'll take a couple of readings around each of those persons and get an average number for your effective draft temperature, an average number for your local temperature and the air velocity, and we evaluate what will be the effective draft temperature around each of those persons as they are seated, where they are seated. Your air conditioning system is already in place, and we know that the control temperature, so we calculate what is the effective draft temperature for at each of those locations. And after we do that for all the 30 locations, we will get what the answer is. And if we find that in 80% or 90% of the cases, the answer lies between the stipulated numbers that we talked about, that's -3 and +2, or between -1.7 to 1.1 degrees Celsius, then people are assumed to be comfortable. Why do I use the word assume here? I'm using the word assume because the existing ADPI formulas don't factor in clothing levels. Okay, that's the only reason. So it's expected that everybody would dress appropriate to the situation they are in. So if we find that 70 to 80% of the people are 70 to 80% of the results lie between those two numbers, then we say that the ADPI of that particular system is 70% or 80%, wherever that lies. Okay. Now, typically, this can also be assigned to the kind of air terminal that you're using. So, if in that particular situation, if you find that the ADPI arrived at is about 80%, then we say that the terminals which are used there are able to provide you an ADPI of about 80%, whatever is calculated. So, typically for mixing air systems or for any other devices, these kind of data gets collated by manufacturers, and you will find that there are certain types of outlets which inherently produce a much higher ADPI than other outlets. The reason for that is some of these outlets, as we go forward, we'll have a look at a few of these outlets, have a method by which they are able to provide you a better control in which the air will move into the occupied zone and get distributed. So let's try and see what they are. So this is what we talked about, that so that's what I mentioned. The ADPI is really taking into consideration just two factors. One is it measures the temperature and measures the velocity. It doesn't look at what the dry bulb temperature is, or what the radiant temperature is, or what the relative humidity is, or how people are clothed. So it just tries to correlate the effectiveness of a velocity with respect to a temperature, and then tries to convert that into a factor to provide a method by which we could evaluate how the system is performing. So let's look at the various types of systems that are available to us to distribute air within the occupied space. We've got 4 types of systems which are normally used. Mixing air systems, which is what we use most of the time. In fact, most of the air conditioning systems that you are working with in our part of the world would generally be a mixing air system. You also have displacement systems, you have unidirectional airflow systems, and you have underfloor air distribution systems. So these are the 4 types of systems that we will be looking at today. Briefly give you an introduction to what they are all about. When we're talking about underfloor air distribution system, this should not be confused with situations where we are trying to supply air to a server farm or a data center, where we tend to supply the air from below the floor. That's not the kind of system that we're looking at. So let's get into it one by one and try to figure out what these various types of systems are and how they differ from each other, and how you could try to see what works best for you. So in the mixing air system, we have 3 fundamental characteristics. One is that the conditioned air is discharged from air outlets which are far away from the occupied zone. So when I say occupied zone, what do we mean? The occupied zone is a space which is about, okay, let me just, so if that's my floor and that's my ceiling, my occupied zone would be something like this. So I'm looking at a space, that's my outside wall. So I'm looking at a space which is about 6 feet from the floor level, and which is within 2 feet from exposed walls. So I've got that little cuboid within the space that's being air conditioned, which is where people are sitting, working, playing, eating, whatever they're doing. So that's the occupied space in a sense. And therefore, anything that we talk about with respect to the conditions that we are trying to achieve will be all within this occupied zone. And in case these walls are not exposed walls, but they are partition walls, then we can expand this occupied zone to within 1 foot of the wall. So generally we would be measuring from 6 inches from the floor level to 6 feet to the top of the occupied zone. And why do we normally disregard that 6 inches is because we are generally assuming that we will not be walking bare feet. Remember the back of the neck and the ankle regions are parts of your body which are very, very sensitive, and usually we tend to cover our feet quite well, and therefore we disregard the conditions at that level. But you could typically say 6 feet from the floor level to within 2 foot from the exposed walls, or 1 feet from the partition wall. So that's really your occupied zone. So in the mixing air system, we are saying that the supply air or the conditioned air is admitted into the space from an outlet which is located far away from the occupied zone. So typically in the figure that I just showed you, we would have the supply air being admitted into the space either from the ceiling or somewhere close to the ceiling, which is far removed from the occupied zone. We do not supply the air directly into the occupied zone. The other criteria that we have in mind is that in a mixing air system, the temperature of the supply air or the primary air is considerably lower than the room air. In other words, if we are trying to maintain a temperature of about 75 degrees Fahrenheit in the occupied space, then my primary air or the supply air, the temperature at which it is leaving the outlet would be around 18 to 20 degrees Fahrenheit lower. Now this you will normally get when you do your load estimation. You will find that you will evaluate something called an apparatus dew point, and based on that you will arrive at what your supply air temperature would be. That's really how you also arrive at what is the actual amount of air that you need to supply into the space so that you are able to remove the amount of heat that is actually present there. So if you are going to have to maintain around 75, generally you will find depending if the load distribution is not is uniform, you will find that if you supply the air at a temperature of around 55 degrees Fahrenheit, you will be able to meet your inside conditions. Of course, you could supply it at a higher temperature, in which case the amount of air that you will need to pump in will be much more. So you'll need to do that balance. The third thing that you have to keep in mind is in a mixing air system, you are going to supply the air at a velocity from the outlet which is considerably higher than what you actually want to maintain in the occupied zone. So like we said earlier, in the occupied zone, we are trying to maintain around 50 feet per minute or thereabouts, and we're trying to maintain 75 degrees Fahrenheit. Then at the outlet, my temperature is around 55 degrees Fahrenheit, which is much lower than my controlled temperature. And my velocity at the outlet will be of the order of about 800 to 1000 feet per minute, which is very high. But the reason why we actually do that is that the supply air, as it leaves the outlet, will entrain the room air. This happens simply because that air is traveling at a velocity, and that the jet velocity will create an area of low pressure around the jet, and that will induce the room air to actually mix with it. So what really happens is that your jet is leaving like that from your outlet, and because of the velocity of the jet being higher than the actual room air, it will create an area of low pressure at the periphery of the jet, and that will induce the room air to mix with it. So that's how the jet actually expands, because there will be an entrainment ratio, and that entrainment ratio will ensure that the room air mixes. Now this is encouraged more, or you'll have more entrainment if the velocity of the air is higher. The higher the velocity, the lower would be the pressure, and therefore the higher would be the entrainment. Also, if the delta T is higher, you will have more entrainment. So these two things will decide how well the system gets mixed. That's the whole objective. Our idea is to ensure that we get the air mixed thoroughly. That's why we call it a mixing air system. Remember one thing, we said that the outlets are going to be located far away from the occupied zone. So all that we want to do is to make sure that that mixing happens thoroughly and it happens outside the occupied zone, so that the occupied zone is not subjected to the kind of turbulences and any low temperature. So when that mixing happens outside the occupied zone, all that we want to make sure when we select is that by the time the air enters the occupied zone, it has decayed in its velocity. And how does that decay happen? Simply because it's mixing with the room air, and also the temperature of the primary air has risen up. It has risen up because again it's mixing with the room air. So by the time the air enters the occupied zone, we would have a temperature which is your control temperature, and the velocities would have decayed to about 50 to 60 feet per minute. So therefore, our decision of locating air outlets, where do we locate them, what kind of an outlet we should select, would all depend to make sure that we are able to maintain the comfort conditions within the occupied zone. So depending upon what your mounting heights would be, how your duct system is, we will need to select an outlet to ensure that we get proper mixing, so that the air which is decaying and coming back into the occupied zone has attained a temperature which is comfortable for you, and the velocities are within acceptable limits. Now remember one thing, that in a mixing air system, the entire volume of air is getting mixed. Okay, so whatever pollutants are there in the room are also going to get mixed thoroughly. Of course, you are going to filter the air before it's going through the cooling coil and things like that. But the fact remains that whatever pollutants are there, whatever the pollutant people are breathing in the room, are whatever you breathe out, are all going to get mixed. Okay, so that's something that you need to keep in mind. So this is what we talked about. Now let's look at some of the different types of outlets that you will come across when we are working with mixing air system. All of you would be familiar with these kind of outlets. You've either seen them or used them. So whenever you see outlets like this, you pretty much know that you're working with mixing air systems. So you've got a set of outlets here which have got some louvers. Now these louvers are all adjustable. So you got a set of louvers here which are horizontal, and here you got a set of louvers which are vertical. Now here in this outlet, what you really done is to marry these two together. So you got a set of louvers which are horizontal, and you got a set of louvers which are vertical at the rear. You could have them the other way around. You could have the vertical in front and the horizontal at the rear. It doesn't really matter. The thing to note here is that each of these louvers are kind of adjustable. So you can actually increase the spread of the air whichever way. In this particular case, you can increase the spread vertically. Here you can increase the spread horizontally. So what really do you achieve when you are trying to change the spread? In other words, you are actually playing with the air jet. So by being able to control the spread, you are able to sort of control the distance to which you can actually throw the air. Okay, so you could actually shorten the throw or increase the throw simply because you have the ability to be able to control the spread. And since each of these vanes are individually adjustable, or you want to make sure that they are individually adjustable, you can actually increase the spread from 0 to about 60 degrees on either side. So that gives you a great amount of leeway to be able to control how you are distributing the air within the space. So if you have a device like this, a terminal like that, then you can actually control the spread in both the horizontal and the vertical direction. So really an outlet like this it gives you a very high ADPI because even once you put them up there, you can still, even if there are some shortcomings in terms of our design, we could, with the help of the ability to adjust the amount of spread, we could actually be able to make sure that the air is distributed uniformly and that the velocity in the occupied zone is within your required limits. Then you have terminals which have got fixed vanes or fixed louvers. There's nothing much you can do here in terms of being able to adjust any spread. So you got to live with what you get. So when you use terminals like this, obviously you need to be very, very careful in selecting the outlet sizes, the velocities, so that you get the right amount of throw and proper distribution. So obviously the ADPI here wouldn't be very good unless you select the thing properly. Then you got something called an egg crate device, which is primarily used for return. Then you got some transfer louvers where you want to transfer air from one space to another. Then you got some sealing based devices. These are all sealing devices. This is a typical 4-way sealing outlet, what we call as a diffuser. It actually gives you 4 envelopes, and those 4 air envelopes work on the principle of the Coanda effect. Like I said, as the air jet comes out of the diffuser, the 4 envelopes, they will encounter the sealing surface, and because they encounter a sealing surface, you have a situation where you cannot have any entrainment happening on the top where it is in touch with the ceiling, whereas entrainment will happen at the bottom of the jet because it's exposed to the room air, and because of that, the velocity at the top near the ceiling remains higher than what's at the bottom of the jet, and this creates an area of low pressure on the top, so it tends to push the jet up towards the ceiling and keeps it hugging the ceiling, and thereby it's able to travel a little longer distance. Of course, eventually the friction factor of the ceiling will overcome the pressure, and therefore the jet would then leave the ceiling. But what really happens in that case, in the case of this diffuser, is that because of the fact that the air leaves the outlet and sticks to the ceiling, spreads out, and then comes down, it induces a lot of air movement from the space to the bottom of the jet. And that's really how the mixing happens in this case. And so by the time the air actually descends down into the occupied zone, it has lost its velocity and the temperature has equalized to the room temperature. So again, provides a very high ADPI, close to around 75 to 80%. The only problem here is that it's got 4 distinct air envelopes because the air comes out in 4 different directions. You could actually improve that by using a round diffuser where the air is going to diffuse in a 360-degree pattern, and therefore the ADPI tends to be even better. This is again a plug diffuser. It's a single phase plate on the outside of the inner core. Sometimes you can actually vary the geometry here, the discharge geometry, and therefore you are able to actually control the outlet velocity. So the problem with a diffuser like this and this is that if the air volume drops from your initial design, typically it could happen in case you're working with variable air volume units. So at the turn down situation, when your air volume drops, then the outlet velocity will drop because the geometry on the discharge is remaining the same. Now when that happens, that velocity is not adequate enough to generate the Coanda effect. So then it will lead to what they call as dumping of air. So in such a situation, the cold air would tend to come down like a shower. So if you're standing below the diffuser, you'll experience that cold draft. That's not very comfortable. So obviously, if you're using variable air volume systems, then this is perhaps not the right kind of outlet for you. Then we have, again, sealing-based products here. These are called swirl diffusers. Basically, what we have is a number of slots which are radially cut, and behind that you have some kind of a pattern controlling device. So the air actually comes out in a radial fashion and then it swirls around. And by swirling around, it is able to mix with the room air. So even if you're supplying the air from the top, it does not dump the air down. It swirls the air thoroughly above the occupied zone, mixes it completely, and then by the time the air loses the velocity, it comes down into the occupied zone, the velocity is low and the temperature is equalized. You have some additional devices here which we call strip line diffuser. This is the same as this. So if you see the profile here, this profile is similar to your square diffuser profile. So therefore it again encourages the formation of a Coanda effect and therefore does not dump the air down. So if you want to throw from the ceiling and not have a side outlet, but and don't want to use a square diffuser or a round diffuser, would want to use something like this, you could do this because it again works on the principle of a Coanda. You could have this one way or two way. Like you see, this is the two way, this is the one way, and then you have slot diffusers. Again, these are linear slots, and behind the slot you have some kind of a pattern controlling device which can direct the air to go in one direction or the other, or it could come straight down. So when I'm able to deflect the air toward the sides, I could actually again generate a Coanda, and therefore ensure that the air doesn't come straight cascading down. I could use this if I want like an air curtain. The advantage again here is that I can have multiple slots, so I can adjust each slot individually. So maybe if I've got 3 slots, I could have one slot coming down and the other slot going to the side like that. So typically if you've got an exposed wall with a lot of glazing on one side and you want to prevent the radiant heat from coming in, then you could maybe have the slot nearest to the glass to come straight down, and the others to deflect the air on the side, so that you can take the Coanda and ensure that people are getting cooled without a draft. The only thing that you want to take care is to ensure that the air that's coming out of that slot is not angled straight at the glass, because if that happens, then it can lead to moisture accumulation on the outside and therefore not look very good. Then you've got some devices which are used for throwing air, large quantities of air over long distances. Typically, you will see them in large public areas like maybe airports or malls, large atrium spaces. So in this case, these two devices, if you look at them closely, they are both the same. So the core here can actually swivel around. So in this position, if you can see the profile, they are all sort of parallel. So this actually makes the air go a long distance. It's like a straight jet, just like this. This is a straight jet. So this is what we call as a jet nozzle. Some people call it like an eyeball diffuser or whatever. Basically, it can throw the air over a long distance. This can swivel up and down by about 30 degrees in 360-degree fashion. So you can direct the jet in a particular direction. They can handle large volumes of air, and they're pretty silent. Only thing is, if you are cooling, then you want to make sure that you don't put them up on the top, on the ceiling. Don't dump the air from the top, because being cold, the air is just going to come down like a ton of bricks. So if somebody's sitting down, they're going to feel very uncomfortable. You would want to throw it from the top, typically if you are trying to heat, not otherwise, unless you're trying to use it for return air. But that's a very expensive return terminal. In this case, this core swivels around. So in this particular setting, it can give you a long throw. And when I swivel it around, then it becomes like this. So here what happens is that means this what you're seeing here is the rear side of this core. So here it becomes like a diffuser, and so it kind of increases the spread. So basically what it does by increasing the spread is you're shortening the throw. So this is what they would call as a jet diffuser. Again, you use it in areas where the amount of air quantity that you require is quite large and you want to throw it over long distances. So that's a typical installation of jet nozzles. This is another typical installation that you see nowadays, is the use of a fan in addition to your air being supplied from the terminals here. Now this is a typical swirl diffuser that's being used, and then we've got these fans what are called as HVLS fans. This serves two purposes. One is it is making sure that the velocity in the whatever mixing happens, the air is pushed down into the occupied zone. Now this could do two things. One is we are trying to use the same system for supplying hot air as well as supplying cold air. In other words, heating and cooling from the same system. So when we're trying to heat and supply from here, at that point in time, that warm air will stratify and need not reach the occupied zone. So at that time, a fan like this will help us to ensure that we push the air right down into the occupied zone. So increasingly, you will see this happening in many places. Sometimes this is also put as an afterthought, because the original system was not able to maintain comfort comfort conditions, whatever, for whatever reasons. So this is added as an additional device to make sure that people feel air movement, particularly in crowded areas. Increasingly, I am seeing this in several airports around the country, where otherwise in the hot summer months you might feel uncomfortable, especially when it's when the flights are getting delayed and people are hanging around at the departure concourse. Then this fan comes in pretty handy. So we call them the HVLS fans, and they are able to make sure that there is adequate air movement in the occupied zone so that people feel comfortable. This is an ASHRAE publication, which is the designer's guide for selecting outlets. Those of you who are keen to know more about it, I would recommend that you get access to this publication, and you will have a better insight into how you would select ceiling-based outlets and how you would lay them out, etc. When we're talking about mixing air systems, conventionally we are talking about units which are supplying a constant volume of air, and that air is admitted into the space, it mixes, and that's how we achieve the cooling. Now, in the old days, this is really how we worked, but increasingly, because of the fact that people are getting more energy conscious and you want to have better energy efficiency, we find that, and generally when we did that kind of design, we would really be looking at the hottest part of the year when we are doing our load estimations. So you would pick the hottest day of the year, do your load estimation, and arrive at what's the airflow that is required to keep people comfortable. But as you know that in all air conditioning systems, generally or probably not even for a single day in the year, the system might be operating at capacity. Most of the times it's working at part load. This is true not just of chillers, but it's also true on the air side. So if you actually do a load estimation for the entire year for 8760 hours, you will find that there is a particular point where you require a CFM of, let's say, for a particular room, maybe 1000 CFM. And there are certain parts of the year where you require maybe only 300 CFM. So it doesn't make sense for us to have a system which is going to keep dumping 1000 CFM of air regardless of what the actual need is. So if you want to save energy, then you must figure out a way by which you can actually supply only that much air that is required. And why do we have to focus on this? Because at the end of the day, what is supplying the air to that space? It's a fan. So if we are able to look at what are the advantages by supplying just the right amount of air, then we need to look at what the fan laws are. Now, if you're familiar with fan laws, it's basically there are 3 fan affinity laws. The first law is very simple, that it says that the amount of air that the fan will put out is going to be directly proportional to the speed. The second thing is that the static pressure generated by the CFM is proportional. The static pressure is proportional to the square of the airflow. So the first thing we said is that your speed is proportional to the airflow, and the last thing is that the power varies as the cube of the speed. Okay, so if I take a simple example and I say that let's say I have a fan which is delivering me, let's say 8000 CFM of air, and for that fan to work and deliver 8000, I'm just taking some arbitrary number. So if I have a fan which is running and delivering 8000 CFM of air, and let's say it's consuming 8 kilowatts, and I require, instead of 8000, maybe a part of the year I require only 4000 CFM. So how does it really help me if I actually make the fan do that? Maybe I could just let it run and let the people feel cold or whatever. That's one side of the story. Or I could tell the people that, look, dress yourself appropriately because that's what I'm going to deliver, whether you like it or not. Or I look at the other way. If I require 4000 CFM instead of 8000 CFM, then the actual power I require to deliver 4000 is not 4 kilowatts, but actually what I require is about 1 kilowatt, because my power requirement is going to vary as a cube. So it makes a lot of sense if I am able to reduce the speed of the fan, because If I reduce the speed, I'm going to reduce the power consumption, and my flow is directly proportional to the speed. And therefore, if I reduce the speed and deliver just the right amount of air, I have ample opportunities to try and save money where I can. And that led us to the use of terminal units. And terminal units are typically classified as constant volume units or variable air volume units. And they further get classified as pressure dependent or pressure independent. And they actually regulate the amount of air that flows into the space, and you could do that using different types of controls. You could use an analog control, you could use a digital control, or a pneumatic control. And what you really need is two things. We need to know what is the temperature that you want to maintain, and you also need to know what is the amount of air that is required in that space to maintain the comfort condition. So these are the two parameters that you will need to know when you're trying to work with terminal units. So let's try and see what these terminal units are. A typical terminal unit is simple in design, which is a pressure dependent device, is what we call as a bypass terminal. So what does the bypass terminal do? You have, so that's what it typically looks like. This would be your inlet, and that's your outlet. So the air will enter from here and go out from there. So typically it's just a device through which air passes. You have a little controller here, which is nothing but an actuator. This could be a modulating actuator, and that works on the basis of a input from a modulating thermostat, a typical Wheatstone spray. Okay, so in case in the room we find that we had a normal requirement was 1000 CFM, and to maintain conditions in that space, and so when we supply 20,000 CFM, it will maintain a temperature of around 25 degrees Celsius, and we say that at a temperature of 23 degrees Celsius, we don't want any air to be supplied, but at 25, we need to supply 1000 CFM. So when the room is trying to maintain 25, then if that's your set point, we'll have 1000 CFM going in and 1000 CFM coming out and going into the space. But if we go and turn that thermostat down and say that, look, I need to maintain 24 instead of 25, then really speaking, what it means, what the controller understands is that, hey, look, I was supplying 1000 CFM, and at 23, I don't have to supply anything, but now the guy wants 24. So all I need to do is to supply 500 CFM. So what it does is this actuator here will move a damper blade that will allow 500 CFM to bypass from the top. So it bypasses from the top and goes back into the return air. So in other words, it takes a position which is 50% free area. So from a fully open position to a fully closed position, it goes 50% of the way, and then assumes that 50% of the air is going through. It doesn't really mean at this point in time that it's going 500 CFM is going through. Okay. Now imagine a situation where I've got an air handling unit, and I've got a long duct, and I've got cabin A where I have a unit like this, and I got a cabin B which is 20 feet away. Both are identical cabins, both require the same amount of airflow, that's 1000 CFM each. And in both those cabins, I've got units identical to this, identical to each other. So in the first cabin, when I take the temperature down to 24, the damper will assume a position which is 50% open, and we are assuming that 500 CFM is going to go through. Similarly, in the cabin which is downstream, again the same thing is going to happen, right? The damper is going to assume a position which is 50% open, and we will have, we are supposing that 500 CFM is going to go in. But if you actually go to site and take a measurement, you will find that in the first room, instead of 500, maybe you're getting about 570, 580 or 600. And in the cabin which is downstream, you're probably getting about 400 or 450. So why is this difference? The difference is primarily because the input static pressure at the inlet of the VAV in the first cabin is different from the input static pressure at the VAV inlet on the cabin which is downstream. The reason for that is the static pressure that's available in the duct is going on reducing as you start from the air handling unit. So therefore, this airflow will vary. And therefore, the person even though he thinks that if I put it at 24, I will get 500, doesn't really get 500. Okay, so that's because this unit is pressure dependent. So the closer it is to the fan, the more air it will provide for the same damper position setting. Okay, so this becomes a pressure dependent device. And the only way to overcome this fallacy about assuming that a damper position gives a fixed amount of air is to be able to actually measure the air that's going through. So we have a pressure independent unit. Now this is what a pressure independent unit would look like. Again, you have an inlet and you have an outlet which is going into the room. So here what happens is that we will have a method by which we can actually measure, we do measure the temperature in the room, because that's going to be your method by which a person sitting in the room is going to be able to set the demand. We also add a method by which we can measure the airflow. So how does that work? So this is a device with a short casing, and then you got a device with a long casing, so that you are able to provide some kind of attenuation in case you want. So typically this is what your pressure independent unit is. So this is your unit, you got a damper and you got your actuator, then you will have a controller. Okay, this controller gets input from a set point value, which is your room thermostat or a room temperature or a room unit, room temperature unit, and there is a differential pressure transducer. So what it does, we've got if you look at it closely here, you've got two sets of tubes. Okay, there's one set of tube, both these have got little holes on them. So this has got holes facing the front and this has got holes facing the rear. So basically what it is doing, it is measuring the one in the front, which is designated as plus, is measuring the total pressure, and the one at the rear is measuring the static pressure. The difference between the total pressure and the static pressure will give you the velocity pressure, and that velocity pressure is then used to calculate velocity, because there is a the equation which says that the velocity pressure is equal to the velocity upon 4000 pi the whole squared, where velocity is measured in feet per minute and the velocity pressure is in inches of water column. So you have a direct relationship between the velocity pressure and the actual velocity. And knowing the velocity, having calculated the velocity and knowing the cross-sectional area, we can have an algorithm which can actually directly convert that to the flow rate. So now we have a setup where we know what is the flow rate and we also know what is the temperature. So we could actually program the controller to say that if you want to maintain 25, I need 1000 CFM. If you want to maintain 24, I need 500 CFM, etc. So once that is calibrated, this is constantly measuring what is the temperature and what is the flow rate. And based on that input, it gives a command to the actuator to modulate the damper. So this is what a pressure independent VAV actually works. You could have additional features put in, like you can make it a constant volume unit by having a fan. You have fan powered terminals. Fan powered could be series fan powered, could be parallel fan powered, depending upon how you really want to use it. For those who want to have more detailed inputs into how you would select air terminals, what these are in more details, and how would you design a system which requires air terminals, which are VAV units, please refer to the ASHRAE design guide. This is one of our newer publications. It's out for the last 2.5 years now. So this gives you complete details about selection, applications, controls, how do you commission them, etc. So this is a great publication handover. Those who are working with air terminals or need to know more information, please refer to this guide. So that brings us to the next system, which is what we call as a displacement ventilation system. This is not something which is very new. This has been around for very long, and primarily it's really started in Europe and utilized primarily in industrial facilities, but now it's become quite popular even for occupied spaces. So how does it really work compared to a overhead mixing system? So in the overhead mixing system, we had air being supplied from the top, that is far away from the occupied zone at a low temperature, say around 55 degrees Fahrenheit, and everything was mixing well. And then people in the occupied zone were kept comfortable. So we had uniform temperature in the occupied zone. Now, what happens in the case of a displacement system? In a displacement system, just remember the three characteristics that we talked about in mixing air. We said that the primary air will be supplied far away from the occupied zone. In the case of a displacement, the primary air is going to be supplied directly into the occupied zone. So that means we don't have units installed overhead or on the side wall far away. They are going to be installed within the occupied zone itself. Okay. Now, remember what we said earlier, that in the mixing air, we've got outlets far away, but they're supplying air at a temperature which is much lower than the room temperature. So we were supplying at 55 when the room was around 75. Now here, since we are going to supply the air directly into the occupied zone space, which means the outlets are going to be located within the occupied space, we need to make sure that the temperature of air is higher. So the temperature of air is usually anywhere between 68 to 70 degrees Fahrenheit if you are trying to maintain 75 degrees Fahrenheit. And the last thing is that earlier we had a very high outlet velocity. We had that high outlet velocity so that the air could mix properly before it enters the occupied space. Here, since the air is coming directly into the occupied space, our outlet velocity is going to be very, very low. Okay. So what we expect it to do is to come into the space and stratify itself. And I'll just run a small little video for you so that you get an idea of how this really works. So this is a space here, and then we've got a person who is, this is our thermal load. The cold air is actually entering the space, and because it's colder than the room air, it settles to the floor level and it moves forward because of the pressure at which it is being delivered. And as it moves forward and encounters a thermal load, it creates what's called as a thermal plume. So you can see that this is rising up along the load. So this thermal plume will take the load, move up and go up to the top and stratify there. So you can pick up the return from the top, and that's how the air movement is generated. So long as there is a heat source, you will create this thermal plume and the air would automatically rise up along that and go up. So here is another view of that. Here again, you will find that the air descends into the space and moves out, and that's your thermal load. So you can see it cascading along the floor. It encounters this load and gets heated up because that's a thermal load. And then it's picking up this and it's going up. You can see that very clearly. So you would have your return somewhere on the top. This is located within the occupied zone. There you can see a very nice thermal plume being generated. This is really how displacement works. Again, you got same way. And here you got your thermal load. So this will have a heater inside just to generate a load. And you can create this kind of thermal plume. And this kind of outlets, you know, they just spread the air around, and the air will go around the whole space. Even if there is an obstruction here, it will not stop. It will go around the obstruction. So typically, you might have a space, and you might have a table or a chair or whatever. It will tend to go around and spread and remain there stratified till it encounters a thermal load. So that's important. So you can see that it's actually moving out. It goes around the obstruction. Okay, so you need to place these the displacement diffusers strategically so that it can actually reach out to the thermal load. So you can see here that the person is standing here, and the amount of air that's required it's picking up the load, rises up, and as the cool air is rising up, more cool air comes to go up. So the return is at the top. So the biggest advantage here that you can visualize is that it's got a tremendous amount of flexibility in terms of where do you want to put your outlets depending upon your seating plan. And The biggest advantage, as I said, is if you look at your the fact that you're supplying primary air from down, and then as it encounters the human being, which are your heat sources, it starts to rise up. So the person who is breathing the air in, even in the occupied zone, is getting cool primary air, treated, filtered, unlike the mixing air system where everything is getting mixed up, you know. So therefore what happens is that the actual ventilation efficiency in this case is much better than what you have in the case of a mixing air system. Let's look at the other advantage. Okay, before we look at the advantages, these are some of the applications. They are used practically in all kinds of applications. So that is the part where I'm talking about the ventilation efficiency. So in a mixing, what I'm doing, I'm mixing the entire volume of air. Here, what happens is that the cold primary air comes from down and then it's going up because of stratification, right? Warm air is rising up. So the concentration of pollutants in the return air to the concentration in the breathing zone, we find that in the case of a displacement or an underflow, the ventilation efficiency is about 20% more, which means you can actually use that much less outside air if your local codes will allow you to do that. So when you tend to use less outside air, obviously you're going to save a lot of energy because you don't have to condition the air, the outside air, which might be at a much higher enthalpy. So the lesser the air you condition, the savings in energy is to your advantage. So what we're doing, we're supplying temperature of the air is at about 65 to 70 degree Fahrenheit. The velocity is 40 feet per minute. And so therefore, since your supplier velocity is lower, you can actually make do with a smaller fan speed. So smaller fan speed would mean that your power consumption will be that much lower. The other thing that you want to remember is that since I'm supplying my air at a temperature which is around 65, unlike the mixing where I was supplying the air at 55. So if I'm supplying the air at 55, my chill water temperature would have to be lower than that. So we're typically looking at chill water in the region of about 45 degrees Fahrenheit. So my chiller efficiency in the case of a displacement ventilation, where my temperature of air is 65, so maybe my chill water temperature could be of the order of about 55. So my chiller efficiency is improved. Okay, so that's one source of energy efficiency for me. But remember one thing, that even though my outlet temperature has increased and my efficiency has improved, my tonnage doesn't change. Okay, and why is that? Because the delta T of the air is now going to go up substantially. Unlike the earlier case, my delta T of the air is going to go up substantially, and therefore my tonnage remains the same, though I'm up, but the savings that I'm getting primarily is because of the fact that I'm operating the chiller at a higher suction temperature. So for the same discharge, my chiller operating, compressor operating head is reduced, and therefore I save power. So these are some of the benefits. Not much difference in the way we designed the duct system. It's pretty similar to the way we design our conventional duct system. Only thing is, because we are going to supply the air at a low velocity, we want to make sure that the velocity of the air as it's entering the displacement diffuser or displacement outlet is lower. So that's the only thing that we take care of. Again, there's a wonderful publication which ASHRAE has, which is on displacement ventilation design guide. Those of you who want to look at this a little more in detail, I would encourage you to look at this publication. This gives you a method by which we can actually calculate supplier volumes, the supplier temperatures, and how you would select your outlets and so on. The reason why this is slightly different from the mixing air is because we are supplying air directly into the occupied zone. So for us to calculate what is the actual dehumidified airflow required, I need not factor in the amount of heat ingress from the space above the occupied zone. So that much of heat ingress actually goes into the return air. So that's the return air gain, including the lighting load, etc. So my deunified CFM, which is my total sensible load in the occupied zone divided by 1.08 by delta T, is actually defining my airflow. So then you find that the airflow required is much lower. So therefore my fan size gets lowered, my ducting sizes get lowered. So that's a big saving. So there, that gives you a so all this that you see, which is above the occupied zone, all that heat actually is getting into the return air, which is your light load and all the fabric load, which is above the occupied zone, all gets into the return air. These are some of the various outlets that we use that are available to you for displacement. They could be all placed on the floor or below the floor as well. They all directly into the occupied space. From typical installations, there you have air coming out from below the seats or from that surface there. And that's at an airport. These are your displacement outlets. They could also be placed within the floor. I'm showing this as underfloor air conditioning, which is pretty much the same as displacement, except that in the case of displacement, it is completely stratified. There is no mixing of air that takes place. Whereas in underflow, there is a small amount of mixing that happens where the air is actually exiting the underflow diffuser, and then thereafter it works on a principle of stratification. That's your and now we can have a look at what the underflow air distribution is. Obviously, it's something very similar to the displacement that you saw, except that instead of supplying the air from the sides into the occupied space, we are supplying it into the occupied space from below the floor. So we actually need to create a raised floor, and the condition there is then directly delivered into the occupied zone. You could have some kind of an outlet which is placed on the floor, and return is picked up at the top. So that's what your typical floor would look like. You have these raised floor. These are the elements on which your access floor tiles would be resting. Typically, you would use a 2x2 tile which sits on these pedestals, and a lot of your services also can then run below the floor. All your cabling, etc., can all run below the floor. It works very similar to the displacement, as I said, and in the cooling applications, the air movement is very efficient because you have the cool air coming from below the floor. Then it gets warmed up because of the thermal loads in the space, and it will simply go up. So you don't need additional fan power to push the air up, unlike in the mixing air system. Obviously, you don't want the air to come up the home of a jet, so you need to have special devices. This is really how it happens. So the air will come out of the jet. You don't have a very high velocity jet that comes out. It kind of comes out and it's like it's a small swirl diffuser. It swirls the air and then allows it to spread on the floor. And then it will spread to the floor, and then it will work pretty much like how your displacement was working. The only thing that we want to make sure is we don't place them directly where people are sitting. So we need to identify areas where you can have this. As I said, the air will exit the outlet and spread along the floor, and then be able to reach all the occupants. Major advantage of using this is that since all your services tend to run below, you don't have any overhead duct systems. So if you want to redesign an office or change the layout, it becomes very easy. You can the tile on which your outlet is put, it can be simply taken out and relocated, and it gives you the same advantages of having a better ventilation efficiency as high as 20%. So the saving in energy is really feasible for you, and also the fact that if you got a large the normal height that you might tend to have from the floor to the ceiling, since in a conventional mixing air system you will tend to have an overhead duct, and then you need space to take the return, etc. You need to have that minimum height between the floor and the soffit to the slab. So in the case of underflow, you don't need that much of space. So if it's a large building, when I say large building, I'm talking about a high-rise building, then it is possible to actually effect substantial saving so that you can maybe save a floor or two in the entire building. That will save in terms of your civil construction costs. Okay. So that's what we talked about, the ventilation efficiency. This could be methods by which we supply. Either we can have the entire plenum being pressurized, and then you have these outlets, or if the space is very large and you feel that we cannot pump the air from one end and make it ensure that we are able to reach it right to the other end, we could also lay ducts below the floor and then have them connected to the outlets. Normally I found that even for spaces like 6,000, 7,000, 10,000 square feet, we really don't need ductwork. You can just pressurize the plenum and still get just make sure that the access floor heights are adequate to maintain that kind of uniform pressure. So you save a lot of money in terms of the ducting. Okay. Have to take some special care because remember one thing, that when we are doing our displacement as well as underflow, we talked about temperatures of the air being around 65 to 70 degree Fahrenheit. Now, obviously, this might have one issue, and that is in areas which have got higher humidity. At that supply air temperature, you might not get adequate amount of dehumidification, and therefore you will need to find method by which you can handle the latent load. So you might have to get in treated pressure to take care of the latent load applications. So this is something which is design specific. You will have to address that issue. The other thing that you will need to look at is since you're going to use the floor, you want to worry about what's below the floor. So if you are situated on a particular floor and there's another area below it, and that area is not air conditioned, then you've got to be a little careful because it can lead to condensation on that level, and also the heat ingress that can come because of the mass thermal storage of the structure. So you will have to take care of insulation of the floors so that you don't have these issues. Okay. So typically this is how it is laid out, so that you don't put any outlets very close to where people are sitting. So this will ensure that there is no draft or there is no noise. The other thing that we need to also take care is about the cutouts, because since it's going to come from below the floor, and this is generally the big problem that one encounters when we are doing underfloor air conditioning, is all the cutouts that get made for the various services to come up tend to have leakages. So you want to make sure that all these penetrations are well sealed so that people are not so that there's no leakage. This is something that you got to take care of. So actually, if you look at, we have a wonderful publication again from ASHRAE, which is the Underfloor Air Design Guide. This comes in 2 volumes. So there is one which helps you with the design aspect and the installation aspect, and there's one on commissioning and maintenance. So it actually lists out all the areas of concern which you need to address, and if you actually follow all this very closely, this becomes a very efficient system. So like I said, those who are interested, please look at the Underfloor Design Guide. This is again a publication. It's about 2 years old, and it's now available on the ASHRAE bookstore. Then of course we have the other system, which is unidirectional. This is largely confined to industrial applications, manufacturing areas, clean room areas, etc. So what we have here is that the air flows uniformly in one direction, okay, and then flows out either from this side, or it can go down and then get out. Something like a laminar flow, and ideally these streamlines would be uninterrupted, and we do this largely not from the point of view of human comfort or personal comfort, but more from the point of view of production processes, or maybe you're working in an operating room where we want to make sure that there's no cross flow or cross contamination of air. So in that case, we want to make sure that the air flows from one side to the other and not the other way around. Typically, for example, in a paint booth, that's another area where we want to have uniform airflow from one direction to the other. So you could have airflows like this. So you can see that the person is working here and there is airflow in one direction picked up the bottom and then it gets recirculated, or from this side it comes in from here and then gets picked up and goes out of the other side. That's about unidirectional airflow. I also want to tell you a little bit about thermal beams. Thermal beams largely work on the concept of, it's something like a radiant cooling kind of situation. But here we have a coil that's a chill water coil, or it could be a hot water coil, depending upon where you locate it and whether you're trying to heat or cool. That's why we call it a thermal beam. I don't want to call it a chill beam, though many people normally refer to it as chill beams. So if you're cooling, yes, then it's called chill beam. What happens is that there is water circulating within this coil. It's a conventional cooling coil, and since there's cold water circulating in this, the air around it gets cooled, and because it's cold, the air tends to go down, and as it tends to go down, it creates a kind of a convective current, and that's how the airflow will continue to happen. So this is what we call as a chill beam or a chill ceiling. So it's put up there, and the natural convective process gets set up, and that keeps the air moving from goes down, comes up again, and that's how the cooling wave works. Obviously, it requires no fan power, but it's got a little limitation in the sense that you don't have any great perceptible air movement. So that gets, and also the fact that remember you're kind of recirculating the same air, so there is no fresh air or anything like that coming in. So in that sense, that's a bit of a disadvantage when you tend to work with passive chill beams. So we have something called an active chill beam, where what we've got is again the same coil, and we got a central primary air duct which comes in above this coil. I'm just showing you a sectional view of what a thermal beam or chill beam would look like. And this air is actually dehumidified, it's treated fresh air, you want to call it that, and that's blown into this void by means of small jet nozzles. So as I explained to you earlier, if you have a little nozzle that's blowing air at a velocity, it creates an area of low pressure. So since the air is coming out at a higher velocity here, it creates a bit of a low pressure area around that jet, and that induces this room air to rise up. So this room air is obviously warmer, so it tends to rise up. It goes up through the coil, and as it goes up through the coil, it mixes with this cold primary air and comes out. And this is kind of angled up in such a way that you're able to really generate a Coanda, and therefore the air doesn't dump down and it mixes. So this way it's able to take care of the latent load, it's bringing in fresh air. And the only problem that we will have is that, all of you are familiar with what happens when you circulate chill water through a coil. It sort of causes humidification. So because of that, you have condensation, and then you want to worry about what you do with that condensate, how do you take it out, etc. In the case of a chill beam, which is going to be directly installed within the space above the occupied zone, it becomes very cumbersome if you want to drain out these coils. So all we ensure is that these coils are always operating above the dew point. That's a specific control that you want to maintain. So it does call for an elaborate control mechanism, whereby we ensure that the temperature of water that's emitted into the coil is such that the coil dew point remains above the dew point of the room. So you don't have any condensation taking place. Okay. And the latent load is primarily, so basically then this becomes a sensible coil. And the latent load in the room is generally taken care of by the treated fresh air that is admitted through this duct that's coming from outside. So that's really how it works. And so that's a chill beam which is set up. This is a chill beam under test, and so you can get an idea of how the air flows. So there you can actually see the airflow. So it actually comes, so the return air actually goes up from down here, and that's how your air, which is the return air, is actually mixing with the primary air, and then it gets discharged back. So you can see that again. So you need to have this sealing so that that Coanda effect is happening, so the air doesn't dump down. Okay, so that's for terminal units, and these are some of the references that actually brings me to the end of this small presentation. These are apart from the publications that I talked about. I would also like you to look at the following chapters. Actually, the new application handbook, which is the 2019 edition, which is now available online. The chapter number is 58. This was the earlier print edition. The last edition, which was 2015, but the latest edition, 2019, you can read chapter 58. The other chapters are from stay as they are, chapter 20 on both fundamentals and equipment. So that's the additional reading for those of you who are interested to know more, and that's my contact details. So any of you want to reach out for anything that you want to know more, please feel free to do that. And we can take some, we have about 20-25 minutes left, so we could take questions at this point. So what I'll do is I'll actually look at the questions. And then I'll try to take them. So if there are any questions, I can. Okay, so can I ask Indrani just put up the questions there, please? Indrani, can you help me with that questions? Indrani, can you hear me?
Yeah, is that air velocity is applicable for cooling of machine, etc.?
Can I have questions here on the screen? Indrani, can you just put them up for me here? So I can just take the questions straight away. Okay, I can't get her here, so if somebody wants to ask a question, just unmute yourself and ask me the question, then mute it back, and then I'll be happy to answer them. So if you could tell me your name and ask me the question, I'll be happy to address it. Anybody who wants to go first? Okay, I see some questions. Somebody's unmuted themselves. Can they just mute themselves? So I'll just take the questions from here. Okay, so the first question from Hariswar Reddy, it says you'll be able to share the PowerPoint. Yes, I can. All you need to do is to get in touch with the organizer, and they'll be happy to share it with you. Then Will we have the recorded session? Yes, the session will be recorded. Please contact the organizer. Same question again from Michael. Will we have the materials? Yes, of course. It's available for sharing. And if you're not able to get it, you saw my email ID. Just reach out to me and I'll be happy to mail it out to you. So most of the questions that I see here are pertaining to the material. So there is a question here which says, why would you require to calibrate for a pressure independent VAV in terms of CFM versus room temperature? That's from Gautam Baliga. Okay, Gautam, the reason why we actually want to calibrate is that we need to let the controller know what is the minimum flow and the maximum flow. So these are the two parameters we want to let the controller know, so that when we do a set point, it's able to analyze what's the amount of airflow that it requires for a maximum temperature and a minimum temperature setting. Otherwise, if you try to work with just the temperature input, you will there's no point in us just measuring the airflow unless we are able to give that information to the controller. So that's the reason we actually have to calibrate to let the controller and hard code these details into the controller. The percentage opening of the damper is correlated to the temperature. Okay, I hope that answers your question. Then which criteria needs to follow to avoid condensation on air devices? If you're talking about condensation happening on your terminal devices, that's your diffusers, grills, etc. First of all, you want to make sure that there is no outside air impinging directly on the terminals, because the terminals will be at a temperature which is closer to the room temperature. So if you've got moisture laden air coming from outside and hitting those terminals, there is a good chance of condensation happening. And also you want to make sure that the airflow out of that terminal is actually happening over the entire cross section of the terminal. Sometimes if the connection to the terminal is improper, you will have airflow not happening over the entire outlet area, and that can sometimes lead to a little bit of condensation happening in the ends. So make sure that your collar connections are proper. So this actually question came from Qasim, and he's unfortunately left. Then Qasim also asked a question, which certification needs to be checked from the manufacturer? It depends on the kind of outlet you're using. All you want to make sure that all the terminals are rated as per standards. Most terminals get rated as per ASHRAE standard 70. If you're looking at VAV terminals, you could look at AHR 880 certification or the ASHRAE 130 standards. These are some of the standards which are available for testing. Then the question is, where underflow is distributed systems are used by Bhagyashree. You could use underflow air distribution for any comfort application. Like I said, all you want to make sure is that you have a method by which you can take care of the humidity requirement. There's no reason why you can't use it even for a normal comfort application. When do we use Amir Ibrahim? When do we use a ceiling swirl diffuser? Any time you want to supply air from the ceiling, that's a ceiling-based air distribution system. You can use a swirl diffuser. You can use it in place of a conventional four-way square diffuser or a round diffuser. The type of swirl diffusers that I showed you are typically used for ceiling up to a height of about 4 meters, but you get special variable adjustable swirls even for larger heights. So you can use it for any mixing air system, even for heating. Okay. Vivek Vani's question is, what will be the delta T value for unidirectional airflow system? Vivek, there won't be any specific delta T number here that I would ascribe. We would use unidirectional airflow only because your requirement calls for it. It's got nothing to do with delta T, depending upon if you want a laminar flow or if you want airflow to flow from one direction to the other so that there's no cross contamination. That's the criteria. Then Aditya says, what type of diffusers are recommended in ICU? HEPA filtration is, if HEPA filtration is not there, What you want to ensure in ICU is to make sure that the air terminal is located. You could use a four-way diffuser or you could use a grill. Make sure that the air draft is not coming directly over where the patient is resting. And you want to make sure that the supply air and the return air are adequately spaced out, so there is no short cycling. Obviously, in a ICU, you wouldn't be putting a HEPA at the terminal, so any outlet can be used. Make sure that there is no direct draft on the patient. Then we've got what may lead me to use active chill beam system rather than mixing system. Oh well, first of all, the active chill beam system is going to cost you a lot more in terms of the actual equipment and also in terms of the control systems. But what it does provide is for a much quieter system. And the fact that, remember one thing, that you're basically using water to carry the heat. In case of air, you're supplying air into the space, and that air is taking the heat away from the space. Whereas in the case of a chill beam, you are using air for the last mileage, but largely using water to carry away the heat, and the thermal conductivity of water is much better, and therefore it makes sense to use chill beams. Question from Tapan Basu: what is a thermal diffuser? Well, a thermally powered diffuser is a diffuser which has got a device which is able to control a damper at the rear of the diffuser. It generally works on a thermal element, and that thermal element has a property that it melts at a particular temperature, and it becomes solid at a particular temperature. Usually between 70 Fahrenheit to 78 Fahrenheit is the range at which these thermal elements work. So at 70, it is actually solid, and at 78, it becomes a liquid. So the expansion and contraction is actually used to move a piston, which can transfer that linear motion into a diffuser which can open and close. So that's a thermal diffuser. What is the recommended air outlet for air showers? Air shower, generally you will have nozzles, which is that you need any device which can actually pump air at high velocities, because the idea is to wash the person down. So any kind of nozzle is good. What is the minimum height? One second. What is the minimum height? One second. Okay. So what is the minimum height above which we need to use jet diffuser? Aditya Vibhute's question is, what is the minimum height above which we need to use jet diffuser? First of all, Aditya, you should never use a jet diffuser if you're going to throw it from the top, especially if you're cooling. You want to make sure that the jet diffuser is installed on the side walls, and you want to make sure that it is installed above the occupied zone and it's not blowing the jet directly into the occupied zone. That's all that you need to take care, because these jet diffusers can be adjusted so that the throw is, the idea is to get a long throw. So you don't want to angle it directly into the occupied zone. So that's what you want to take care of. Then what is the thermal diffuser? We answered that. We answered. Okay, the next question is from Princely Samuel. It says, what's the impact of blow in air diffusion? How do we manage design for that? I am not really able to understand this question, Sam Princely. You say, what is the impact of blow in air diffusion? How do we manage design for that? So I presume what you mean by blow is the throw. Really speaking, you need to know what the throw is. So you look at the catalog and figure out what the throw is to give you a certain the desired terminal velocity. So that's very important for you to know, because without which you can't really select the right kind of diffuser. So that's the impact. Unless, if I'm not making myself clear to you, please feel free to contact me by email and I'll respond to you. What's the difference between passive beam and chill beam? Okay, so I mentioned that There's a question on air curtains. I'm sorry, I'm not really able to answer that question on air curtains for you. But if you look at the last edition of the ASHRAE handbook on equipments, we have a full chapter. It does cover the air curtains, so please look at that. The difference between passive beam and active chill beam, the difference is that in passive beam you don't have any supply air being brought in from external side. There's no treated air. In the active beam there is treated air being brought in, and that's how the system is working. You saw it in the video. What is control temperature? Control temperature, question by Aditya, is that it is a temperature which you are setting the room at. So if your set point in the room is 75, that's your control temperature. What is CAV? Tapan Basu, the CAV is constant air volume unit. Sometimes what they do is you want to maintain a constant flow of air in a space. So typically you will use a fan powered terminal. So what you generally do is use a series fan powered terminal box where the fan is running constantly. So depending upon the temperature that you want to maintain in the space, it shuts the primary air damper will shut off, and the balanced air is picked up and mixed with the supply air and then supplied into the space. So you maintain a constant flow of air within the occupied space. Question from Abhishek, what is air cross-section velocity in mixing system? I don't get this question. What is air cross-section velocity in mixing system, displacement system, and chill beam system? Abhishek, I'm not able to understand this question, so can't answer that. Then there's a question from Santosh Indulkar. It says, what's the difference between a grill, diffuser, and a register? A grill is a device that you would normally put up on a sidewall. A diffuser would go on a ceiling, and a register is any outlet with a control damper would be called a register. Kanwar Singh says, what instrument would you measure the velocity of air when you are working towards ADPI or while calculating draft velocity? Would a hot wire anemometer be required? Well, Kanwar, the hot wire anemometer is expensive, but it's a good instrument to use. Anything that you can measure accurately is what I would advocate that you use. Typically, you could use a hot wire anemometer. People generally tend to use a vane anemometer, but a hot wire anemometer is something that's far more accurate, though more expensive. Suresh K says, what happens if the ADPI arrived after cooling load calculation be less than 50 degree Fahrenheit? What will be the minimum requirement of ADP temperature? Honestly, Suresh, there's nothing like a minimum requirement. It will all come out from your load estimation sheet. So there's nothing like a minimum, I guess. You will, depending on your load estimation, depending upon your sensible heat component and the latent heat component, you will arrive at what the ADP is. So next question is okay, there is we will need to, what about pressure drops and noise levels across? Okay, 1 second. There is Subbu says, what are the certifications that we should look for by selecting air terminal, say diffuser or grill? Well, Subbu, the certification, as in you need to make sure that the ratings that you're looking at on a product catalog are based on some kind of standard. And typical testing standard for air outlets, I would recommend is ASHRAE standard 70. So I hope that answers your question. And then Kanwar says, what about pressure drops, noise levels across terminals? Yes, of course, Kanwar, you're very right. Your catalog, product catalog of the manufacturer should give you pressure drops, should give you noise levels, should give you throws, etc. Without which selection becomes difficult. Then there is Yash Karkhanes who says, we will need to regulate AHU fan speed in the system with multiple pressure independent VVs connected to a single AHU. How do we ensure air volume is required as per demand? Well, actually, what happens is that you need to have a method by which you will control the fan speed. As the VAVs in the pressure independent system start to close, the pressure inside the duct will start to build up, and you will therefore need to have pressure transducers inside the duct, and then that will be giving an input to the AHU fan to regulate the speed. And that's how it is done. You can have different algorithms by which you do this. You can have either multiple. Earlier we used to have a practice where you kind of put it, 2/3 of the way down the longest duct. But the current ASHRAE recommendation is that you go 75% of the way. But there are different methods by which it is done. You could have a pressure transducer put at the outlet of the AHU, and then set the static pressure and keep resetting it so that the last VAV at the most critical line is always open to deliver the required air quantity. So there are different methods. So then there is somebody who says videos on mixing air systems. Well, I don't have it in this presentation, so can't help you with that. Majid Amri says he would like to have documents on chill beams. Well, there's the REWA chill beam design guide. Majid, you want to refer to that? That will give you a lot of information. There is Rudra Pratap Aditya who says, then how to go ahead? I'm not sure what is it he's talking about. The question is incomplete. Gaurav Bhatt said the video we have seen is just because of difference in temperature of air and obstruction, or there should be some effect of viscosity property of air as well. Now, which video are you talking about? Are you talking about the displacement video? In the case of a displacement, what's really happening is that the air is exiting the outlet, and because the fact that air is at a temperature which is lower than the room temperature, and because of its density, it just kind of settles to the surface and gets pushed forward. And as it encounters a heat source, it gets warmed up and starts to rise. So that's really how it works. There's no other property that you need to worry about. Ragumuttu Kumar, he's left, so I don't take that question. Then there is Ibrahim Muhammad says, thanks to the organizer, please, how do you present dirts entering the air terminal in the case of underfloor duct? Well, okay, Ibrahim, all these terminals that you put on the underfloor, these are very special devices. You just can't put a normal a grill or something like that, because these devices actually come equipped with a good swirl grid on the top. They are made of die-cast aluminum, and it's got a dirt trap at the bottom, so you can remove the core and clean it out on a regular basis. So that's really how those diffusers are designed. They actually do come with dirt traps which can be removed and cleaned. Then there is a question by Bijoy. He says one of our projects, the HU installed is very old and motors are incompatible with BFD. So that in case, can I use BFD bypass to facilitate proper airflow? Well, actually, Bijoy, when you're using a bypass VAV, remember one thing, that you are only providing some sort of a control at the occupied zone level. But as far as the system is concerned, it's handling the same volume of air. So there's no energy saving per se that's going to accrue to you. So really, you need to check whether you want to do all that. Okay, and like I said, you want to also make sure that if you're going to retrofit, then you want to make sure that the AHU is the fan has got the capability to generate adequate static that is be required at the entry of the VAV boxes wherever they get located. So that's a calculation that you will have to do to check that the fan has adequate capacity to be able to push the air through. So Joyce's question is repeated. He repeated it again. Aditya says, how about cleaning of floors in the case of underfloor cooling? Well, Aditya, that's the easiest thing to do. Remove the tiles, use a vacuum cleaner. Remember one thing, that this is a big advantage of underfloor. You can't clean what's on top of the false ceiling, right? That's impossible to do. But in underflow, that's why it's much cleaner and much better. So cleaning is very easy, not a problem. So then the other question was, I'm not getting displacement ventilation easy is left anyway, so I don't bother. How to measure pressurization of the space to the ambient? Well, you use a gauge, simple. How to calibrate minimum airflow for the VAV in order to maintain proper pressurization within the space? How do we calibrate is in the sense these are calculated numbers. When you do your heat load estimation for the entire year, that's when you'll arrive at what your maximum flow is and what the minimum flow is. So there is a certain time of the year. For example, you might be having an office which is working 24 hours, 365 days. So in the winter, in the night, you will require say 500 CFM per particular space. But in summer, for the same space in the afternoon, you will find that you require 1200 CFM. So that's really how you determine what's the minimum and maximum. And once those numbers are established, that you simply use that to calibrate the airflow. Then the question from Taqiyuddin Syed is how sound attenuation of VAV boxes to be addressed. Any VAV has two types of sound that you need to worry about. One is your case generated noise, and the other is your discharge noise. As far as discharge noise is concerned, what you could do is you can go for an extended case unit, acoustically line it from inside, and also you have downstream of the unit, you will have some length of duct and a terminal. So all that also provides attenuation. For case regenerated, again the idea is to use a good quality insulating material within the unit. That takes care of it adequately, and generally you will have VAVs and then you'll have a false ceiling, etc. So generally not much of a problem. Recommended sound level while selecting air distribution terminal. Well, Sunil Kumar Reddy, the recommended sound level will have to come from your customer. What is the NC level that he would like to maintain in the space, and then you will look at your selection catalog for the product and select a product which will meet that NC criteria. Rudra Pratap, sound level dB going to affect selection of diffuser. How to go ahead? Well, Rudra Pratap, my answer is exactly what I mentioned for Sunil Kumar Reddy. You must know what is the application and what is the sound level that you need to maintain. Generally, these are given in NC numbers, or what is the sound pressure level required. And the catalog will give you either the NC number or it will give you a sound power level. And based on that, you will have to select the appropriate terminal. Then Raibole is left, so I don't take that question. Okay. Abhishek Jain has left. Then Ashok Das, could you throw some light on induction factor of air distribution products? When you say, Ashok, when you're talking about induction factor, I presume you're talking of entrainment. So entrainment ratio really is actually external to the device. So depending upon what is the outlet air volume, what's your velocity, it's easy for us to calculate what the actual entrainment ratios are because there are simple formulas available for that. Pratik says, we do not see any mention of return at terminal position. Why so? Surely it will have an effect. Yes, of course, Pratik, I did specifically talk about return air. Suffice to say that we want to make sure that our return air terminals are again selected based on return air ratings and not based on thumb rules. We want to make sure that they are located in such a way that we do not have direct air moving from supply towards a return. So we need to look at the layout and then position them accordingly. We want to make sure that you select it based on the criteria of what is the actual amount of air that can be extracted depending upon what is the negative static that's available behind the grid. So please look at the catalog and select. Yes, but I didn't specifically mention it. Tirunavu Karsu says, kindly tell all to unmute. Okay. Bhagyashree's question is, there are suction fans sort of at the outlet to suck air at high velocity. I'm not very clear about this question, so can't take it. Salman says, is there any relation of NC level with higher outlet velocity of? Well, Salman, the higher the outlet velocity, the higher is going to be your noise level coming out of the diffuser or the grill. So you want to select, when you do the selection, you have to look at all this together. You need to look at the outlet. The outlet velocity will decide what your throw is going to be, right? So you need to look at the outlet velocity, you will need to look at what is the NC level, and you will also need to look at what the pressure drop is going to be. Because the higher the outlet velocity, the higher the noise level, the higher the pressure drop. So you want to make sure that you select the optimum situation. So that's the correlation. Bhagyashri says, is that air velocity is applicable for cooling of machines, etc.? Well, I'm not very clear about this question, so I can't answer that. Rudra Pratap has left. Sudhir Mathur, is passive chill beam have a blower? No, Sudhir. Passive chill beams are just that. There is it is relying purely on convection. Somebody called Girish's question, he has left, so I don't take it. Majid Ambi says, is it mandatory to use HVLS fans? Where is that question? One second. Is it mandatory to use HVLS fans for large air volumes, or what are the typical conditions application where we need to insert this in addition to air distribution terminal? Well, actually, HVLS really stands for high volume, low speed fans. So it's not that I can't tell you that this is a particular application that it can be used or not. So sometimes, like I said, it can be pre-designed that you will have a certain amount of air coming out of your supply air outlets at a particular temperature, and you can increase the velocity in the occupied zone by going in for HVLS fans. So we talked about right in the beginning that if we are talking comfort condition, it's not necessary that we have to have a lower temperature and lower velocity. We could have higher temperature and higher velocity. So use it discreetly. Salman says, is air quantity required in displacement ventilation will be more? No, Salman. Actually, the dehumidified air quantity is much less than in conventional mixing system. I told you that how we do the load estimation. So we are only taking the heat input that's coming into the occupied zone. So therefore, the dehumidified CFM will be less because your numerator, where you're putting the room sensible heat, is going to be lower. So therefore, the actual air quantity will be lower. Mohammed Shanan says that increasing the supply air temperature and displacement to 65, will it affect humidity removal? Yes, of course it will. That's why the caveat that in areas which have got higher humidity, you want to figure out how you're going to do this. Would you have to have reheat? These are the aspects of design. Obviously, since you're going to supply air at 65, the coil by itself will not be able to remove that much moisture. So you might have to add reheat. So that's why I said look at the design guide and figure out how to do that. Akbar Zahir, hi Akbar, UFAD, do you have the challenge of having more ducts to handle? Not necessarily. Like I said, most of the cases we are able to make do with just pressurizing the plenum. But if your floor area is very large, then you might have to use ducts, but it's not a problem at all. It's much easier than using conventional overhead mixing systems. Omar Abro says in displacement, isn't a higher supply volume required since the supply temperature is reduced to maintain the same load? No, actually, Omar, that's what I said, that your actual load is going to be lower because most of the load in the room that's above the occupied zone is going to go into the return and heat gain. So therefore, even though the delta T on the dehumidified heat calculation is lower, your room sensible heat component in the numerator is lower, and therefore you will be having a lesser amount of air to deal with. So Ashok Patel's question is again answered earlier. How is the return air routed? The underfloor, what we do is the air comes into the space from the floor, and then it gets warmed up and rises up. So there is a little bit of mixing taking place at the floor level, and after that we are relying purely on stratification. The warm air would rise up and we collect return air at the top. So therefore there is no additional fan power required to push the air up. Abiola, if you're supplying air at a high temperature for displacement ventilation, how then do you control humidity? I already answered that question. Terminal velocity is increased to Princely. Terminal velocity increased to 800 to have better entrainment. What will be the impact on air noise? Yes, that's right. So therefore, Princely, what we need to do is to look at the catalog and make sure that we select the right outlet size so that we are able to balance both the requirements. We need to balance the requirement of not both, actually three. We need to balance the requirement of throw. We need to look at what will be the noise level and also what the pressure drop is. Because as we increase the velocity of the terminal, the outlet velocity, then your pressure drop is going to increase as well. So we got to factor in that also. If duct is designed at more than 1500 feet per minute, what should be the FPM of the grill? Grill temperature will be 27 if duct is designed at more than. Well, please remember one thing, that don't get confused between what is the velocity of the air inside the duct, because inside the duct the velocity is simply divided by the cross-sectional area of the duct. Whereas at the terminal you have to look at what the effective area of the terminal is. The effective area is a function of not just the cross-sectional area as you see it, but it factors in things like coefficient of discharge, etc. So therefore the effective area is much less than what you actually see, and therefore the outlet velocity tends to increase automatically because of coefficient of discharge, etc. So that's taken care of. Then Raghumotu is left, Pindu is left. Kishore Kumar is left.
Hi,
Yes.
sir. I'm Indrani here. It's already time is over, so everyone can ask questions on the link shown or the mail ID Mr. Kishan has shared.
Yeah, I think that would be good, because I think we have exhausted our time, have we? Yeah, it's actually 6:02. So I couldn't answer all the questions, but what I will do is I will do two things. One is all of you have my email ID. So any questions that you've already put in or you have additional questions on any of this presentation, please feel free to email me and I will be able to communicate with you. The other thing is I will send a copy of this presentation to the organizer, and any of you who wants a copy can please get in touch with the organizer, and they'll be happy to send it out to you. So you will have all the slides. I will send out a copy. Please feel free to use it. That's ASHRAE material, so I have no issues in sharing with that. So I want to thank all of you for coming by. It was wonderful talking to all of you. I hope I was able to give you some insights into the current trends in room air distribution, and happy to talk to all of you. Thank you very much, and also thank you to Indrani and Shailendra and the host chapter for having me on this presentation. Thank you very much, and God bless.
I also thank everyone. I also thank everyone, the participants, and Shailendra, Osama, Mr. Krishnan. Thank you so much for such a nice session. Bye.
Thank you.
Thanks, sir. Thanks. Today, more than 330 participants have joined.
Thank you very much. I'm happy
Yes.
to see the gathering, and hopefully you will have more successful programs in the future. Thank you for doing this.
Yeah, welcome.
Thank you so much, sir. Okay.
Thank
Bye,
you.
everyone. Thank you.